All right, in this problem we're asked to rationalize the denominator and simplify. We get to assume that all variables represent non-negative real numbers. So let's begin. We will start by rewriting this fraction by applying the cube root to both the numerator and the denominator. All right, next our goal is to create another fraction equal to 1, so numerator and denominator must match, so that we can multiply these and rationalize our denominator, or get rid of that cube root symbol. So we need to create a denominator so that when we multiply, we end up with a bunch of perfect cubes underneath a cube root sign. So first we consider the coefficient 3. And what must we multiply 3 by to arrive at a perfect cube? Well, considering our list of perfect cubes, 1 cubed is 1, but that almost never does us any good. 2 cubed is 8, we're getting warmer. 3 cubed is 27, and sure enough, that's one that 3 is a factor of. So we must multiply 3 by 9 to get 27. So I think you get the idea. We're building this denominator to do some work for us. As we build it, I'll keep the numerator up to speed. Now r to the 5th. So we want, well, silently consider this. Now what that should indicate to us is that if we could make an r to the 6th power, well, that's going to have a cube root that works out really well. So what we need to multiply r to the 5th by to arrive at r to the 6th power would just be r to the 1st. Now t to the 11th, we'll do something really similar. Let me clean up our page just a bit. But we'll do something really similar to arrive at t to the some exponent that 3 is a factor of. It needs to be greater than or equal to 11. It must be 12. So we would multiply by t. We already have t to the 11th, so if we multiply by t to the 1st power, well, we get t to the 12th, and that's what we're looking for. So here, I let our numerator fall a little behind. Here's what we want to multiply by, numerator and denominator. So let's see what happens as we do that. I think I've got enough room here. We'll give it a shot. So for the numerator, we'll end up with the cube root of, and I'm just going to multiply the radicands from the numerators. That's an S in blue there, not a 5, so don't be confused by that. We have a 9 for a coefficient. I'll put the variables in alphabetical order. So the r, then the s to the 17th power, and finally the t. Getting near the edge there, maybe I'll write a little smaller for the denominator. But what we're going to get for the denominator, it's really where the magic happens. We end up with the cube root. 3 times 9 is 27. R to the 5th times r is r to the 6th power. Looking good. T to the 11th times t is t to the 12th power. Moving on, as we continue to simplify, the numerator is not really, well, it's not our focus right now. So while we'll do a bit of simplifying with the numerator, for now, let's just leave it as the cube root of 9rs to the 17th power times t. The denominator, on the other hand, the cube root of 27, 3. The cube root of r to the 6th, r squared, and the cube root of t to the 12th, t to the 4th power. This is looking great. As we continue, well, we apply the cube root to 9. That doesn't simplify nicely, so we're going to have to leave a 9 underneath the cube root. R, well, it's r to the 1st power, so we couldn't factor out an r cubed S to the 17th though, we're going to have some number of s's, or some s raised to some exponent here and here, but let's figure out how that works. So we're kind of back to this idea of elementary school division, when you were still allowed to use a remainder, or modular arithmetic, if you want something a little more advanced in elementary school. So we want to know, how many times does 3 go into 17, and what would the remainder be? So if we thought about 17 divided by 3, we find 5, remainder 2. So that's really how many groups of s cubeds we could factor out of s to the 17th, and we'd have to leave 2 underneath the cube root sign. So the 5 goes here, and the 2 goes underneath the cube root sign as the exponent of the s in there. And finally t, because it's just plain old t, there's nothing we can do to factor that out. If I clean up down here to make a little bit more room. Pardon the interruption, but I'm back. Where were we? I think we were about to write in a denominator, which is already rationalized and already in its simplest form. So we're almost done. 3r squared t to the 4th power. Yeah, it looks good. Once you think you have your final answer, it's always a great idea to double check some things, take a step back and think, is there anything else I can simplify? Are there any more perfect cubes that could be factored out of our numerator? A good example might be, in a result like this, let's pretend for a moment we had a 6 here. Well, that 6 and 3 could work together to reduce the fraction, but we don't, so we can't reduce that way. But that's the kind of thing to be mindful of. Cube root of 9, can't do anything with that. R, s squared, t, and the denominator. I think we've got it.